Okay, friends, welcome back and good afternoon. Uh, well, we are going to start the last session of today's afternoon. The last session is a tutorial given by Sara, Saeedi, Madani. Thank you.
So, okay, so we continue as yesterday. You were probably into general groups. Now I just want to say the beginners of yesterday, I can suggest them to do. So if they are done with their yesterday part, they can go, of course, to non-beginner part of yesterday. I hope you have some pictures of my board from yesterday. Plus something new. If you remember in morning, we had a colon ideal with the second square free power. And we said that it is the edge ideal of some graph, which we called it H. And I told you that it's nice if you can describe that graph whose edge ideal is this one. So E was an edge of G, and then this colon ideal. In the morning, we said that this is an edge ideal of some graph H. And if you have your notes from the morning, it's useful if you describe that graph, because if then you want to complete the proof of that lemma that I gave you in the morning, or you want to look at the paper further later, it can be helpful. So if else, just please complete your E part from yesterday. But non-beginners, again for today, first of all, because yesterday stuff could be really useful. So if you are not done with them, I really suggest to go through them and ask me when whatever you want, because this is the last day that I am personally here. Okay. Because then you will be sure that you understood whatever is expected. But then from today's lecture, I gave you a lemma number 3, and I started the proof. I gave you the strategy, but it would be nice if you can complete that proof using this edge that you the graph H that you can describe above. And secondly, I defined this morning the normalized depth function, and I claimed that it is a non-negative function. And I said that it's not difficult. It is not trivial, but it's not also difficult. You can observe it. So please try to show that for any k from 1 to nu, G, I, K is non-negative. If you feel better, you can just work with the edge ideal of a graph. If not, you can take any square-free monomial and do it in general. And as a hint, I told you that, I mean, this is one way to go through the Auslander-Buchsbaum formula, reach the projective dimension, and then attack to that via Huxter's formula, if you know about reduced homologies. So these are the things that I can suggest for the moment. And again, if some of you prefer, instead of thinking, to read something, as a reading suggestion, just Google and see what are Cameron, Walker graphs are, which I just named them in the morning session. You can see what matroidal ideals are, which I said that they have the minimum depths. So you can now extend the literature by these keywords, and also a square-free Veronese ideals. If you are more comfortable to read some new definitions, see some examples, you can now Google those free stuff. Okay. Then this is your choice to do these things or look at these research problems, or you can all have them for later, for the coming weeks. Somehow I mentioned them during the lectures, but as far as I can, I list them in this way. So we had a lower bound. And the lower bound we proved for powers from 1 to nu1. Nu1 was the induced matching number. But still there's a chance that we have non-zero powers till nu itself. So we did not discuss from that point on. So is our lower bound still valid for k from nu1 plus 1 to nu-g? So these powers were not in my discussion. So you can see if you can show that the same bound holds for these powers as well, or you should find another bounds. You maybe find some counterexamples for these, that bound does not work. And also about upper bound. If you remember, we just mentioned k equal to 1, k equal to 2, and the last possible power, nu. But in between, we didn't say anything because we do not know anything. So for k equal to 3 to nu minus 1. If the same upper bound really works, or you should make some changes. So for these powers, we would like to have some upper bound and give some nice combinatorial based explicit formulas, not bounds, for any square free power actually, but especially for the, since we say combinatorial, we are more curious about graphs. So this can be done in two directions somehow for certain case or certain classes of graphs. Both could be interesting. And here we can have or and both. So you may find some, I mean, for the second square free power, we saw that for Cameron-Walker graphs, we have an exact formula. But besides that, there's no exact formula. For forest, later Hebe and Array did something, but it is just for forest. And okay, so about depths, you can, it's not 3, but 4 new classes of square free ideals or graphs in particular with minimum depths or non-increasing normalized depth function or even better characterization. I mean, it's of course perfect if one can characterize all square free monomial ideals whose depth function is non-increasing or it has minimum depths. If not, characterization is possible, but still giving new classes of ideals like metroidal, like Verona's ideals or so. So this is actually 4 different problems, I would say. And finally, at the end of the lecture in the morning, I mentioned a new definition that it's not needed to start with the square free monomial ideal. You can start with any monomial ideal and then take the multiplication of those generators which provide a regular sequence. So based on this definition, look at the more general setting. You mean what I mean? You know what I mean? More general setting, which starts with any monomial ideal and repeat 1, 2, 4. So problems 1 to 4 were specifically for square free powers, and in particular for square free powers of edge ideals. But at the end, if you look at the more general setting to the new definition, you can repeat all those problems. Less is known here for sure. You can do more. Yeah. And then just some people asked me for some good references. I can just suggest some good books. I mean, it's not totally related to square free powers, of course, because they are new topic. But about monomial ideals, simplicial complexes, graphs, resolutions, and several of these two keywords that I am telling you here and several things I can suggest. For example, I mentioned also yesterday, by Herzog and Hibi. Graded CZGs by Piva. Monomial algebras by Rafael Villarreal. And I hope I'm not making a mistake about the title of the book, but I think combinatorial commutative algebra by Richard Stanley. I mean, each of them, I mean, all of them are good, but some of them are good for some specific topics. For example, you can find these two metroidal and square Veronas in the first book. The graded CZGs is more concerned with homogeneous ideals in general, not only monomials. Monomial algebras maybe is more related to graphs. And the last one, I really like it for reduced homology stuff. I don't know why, but I like it very much for that topic. So I think you should have all of them on your computers at least. And I sent Maurice the two main papers that my lectures were based on, plus 4 other papers. And these are some recent papers. I gave him the link, the archive link, for sure we can find the journal version. And I think he immediately puts them on the website, right? And then I don't write the papers here. So you can see on the website, there are 6 papers, I think, right? Yeah, but then the books are here. So maybe now there is no enough time to think about the research problems. But if you wish, you can consider these exercises. And like before, like yesterday, I'm around. Just to let me know if you want to discuss these things or any other thing. Yeah.
And these books are available.
I think so.
Okay.
Maybe not all of them. Some of them, I think, but you can find them for sure in the libraries. Yeah. But they are very famous books. So if you Google them, you can find out immediately how you can have them somehow.
If there are any